I'm Mohammed Shahbaz from Princeton. Today I'm going to talk about our work on customizing OVS using P4. This is a joint work with folks at Princeton, Stanford, VMware, and Barefoot. So the question that we are going to answer in this talk is or going to attack in this talk is going to be about customizing OVS is hard. It requires changes across multiple locations in the source tree. And also, whenever a new change or a new version comes up, then the old changes have to be carried on to the newer version. So, for example, in our experience, like adding a new field required us to actually touch 12 different files in the OVS source tree. And similarly, adding a new action, actually, we ended up changing 10 different locations in the source tree and with multiple locations within a single file. So, also, manual changes are time consuming, as we all know, and they also lead to errors because you are doing this manually and because probably a human is sitting down and writing these changes. So chances are that it might end up in getting some errors, and these errors might not be that obvious. So detecting or finding these errors is not as simple and can actually take up a lot of time. So the question there is what we need here is we need to add new protocols and features, and we want to specify these new protocols and features in OVS. So maybe there's a better way of doing that. So in this talk, we say, why not use a program to specify these changes? There are many benefits in this. First of all, you can rapidly add new protocols and features by just writing a new program, unlike going into different locations and then doing modification and so forth. And also, there, with the program specification, you can also do better automation, testing, and debugging by building better compilers, testing tools, and stuff. And similarly, the issue of doing backward compatibility becomes a bit simple because now instead of moving changes as soon as a new version comes up, you move these changes old changes into the new one. You can just write programs, and then you can assign these programs as snapshots of each new change that comes in. And whenever you want to use a certain feature, you can just go back, install that program, and start using the OVS. Okay, so I think I talked a lot about the benefits of a program, but the question is what language should we use for specifying these programs? So the thing is there are different kinds. So in one of our previous talk, we talked about a CLI DSL, and there are many other things. But the question there is we have to come up with a description that covers most of the basic requirements that we already have or need in the OVS or in a software switch. So in this talk, as obvious from the title, we are going to talk about P4. Can we use it? So P4 is an open source language. There's a lot of work going on in making it open source and adding new features in that language. It's a kind of a language that actually lets you define different aspects of a packet processor. So again, vSwitch in an abstract form can be think of a packet processor. And in that processor, what we need is how do we handle headers and fields? How do we do packet parsing? How do we do different actions? And also, how do we do match action tables as well? Because given a certain match, we want to do a certain set of actions. And finally, one thing that is not very obvious, or maybe it's obvious in vSwitch, is the control flow. But when we talk about a language, and when we say control flow, it's more like you are statically defining that control flow in that language. So in OVS, this thing is not very obvious, as I think in one of the previous talk, the other guy talked about. Okay, so if we think we are going to use P4 as a high-level language, then we need a compiler. We need to compile P4 to OVS. And it has two main aspects. When you are building a compiler, there are two things that you have to look out for. One is there an efficient mapping from P4 to OVS? That's the first question. And the second question is, what is the cost of programmability? Because now you're not doing these, it's just like writing a code in C or some high-level language and writing something in assembly. Definitely something you write in assembly is going to be fast. But the thing is, having a higher-level language actually helps you do rapid prototyping and stuff like that. So with that programmability, what's the cost of that programmability on the actual performance? Okay, so before attacking these two aspects individually, I'm going to give you a brief intro about how I look at the OVS, and then I will try to map different P4 features onto that architecture. So here's a very simple and a magnified view of an OVS architecture. In OVS, again, it's irrespective of whether you're talking about a kernel data path or an OVS TPDK-based implementation or whatnot. At an abstract level, there are two partitions in an OVS switch. One is the fast path, the second is the slow path. So whenever a packet comes in, it goes to the flow extraction block, which is this block actually operates on the packet and extracts the necessary information. So you can call this as a parsed representation of the packet with the necessary set of fields that you want to operate on later on. Then once the flow extraction has been done, you do a cache lookup, again in the fast path. And if there's a miss, you send the packet to the slow path for further processing by the match action pipeline. This is the actual pipeline with multiple tables and all that happening in there. And if there was a match in the cache, you get a hit, and you then select the actions associated with that entry and apply those actions on the packet and send it out onto the egress. And finally, there is a third element, which is sort of like a remote part, but still it works. It is required to actually configure OVS. That's the runtime configurations using OVS command line utilities. So in summary, if you look at this thing, like it's this figure, we have 6 main elements. One is the flow instruction. Again, then we have match action pipeline, actions, flow struct, and finally the runtime configurations. So now whenever you are going to describe any change or feature, it's eventually going to change one of these or multiple of these locations in the OVS code base. So in the next slide, I'm going to talk about how different P4 constructs are actually applied or mapped onto these different areas or blocks in the OVS code base. Okay, so in P4, there is a notion of header, metadata, valids, stacks, and field refs. So these are all different ways of accessing some state in P4, like whether it's a packet-related information like header, or it's something that you actually deduced during the packet parsing or match action pipeline like metadata and other stuff. So all this actually in OVS is mapped onto a flow struct. And then we have parse representation, the way we want to parse a packet. So that description actually maps onto the flow instruction block. And then you move on to the actions. Again, note that these actions are different from the slow path action that we saw in the previous slide. So these actions are actually deparsing, doing checksums, generating a digest to the controller, and others. But these are actually the ones that I picked from the P4 specification. And then we have the match action pipeline in the slow path. Again, there are many different primitives that P4 provides you, like add, remove header, drop, no op, add to field, and modify field. And then finally, we have runtime configurations that take care of the field lists, action definitions, table declarations, and control flows. So again, why? So the question comes up, like, first of all, why do you do these field lists, action defs, table decals, and control flow in the runtime configuration? Because the thing is, these are more like constraints. OVS is already very generic. Like, it can actually match on different fields that can do different actions. So P4, in a way, is letting you constrain the way you can actually use these tables. So this is a similar problem that has been raised in the last talk. Like, the control flow becomes very convoluted or complex when you talk about higher level of applications. So in this way, you can actually statically define the pipeline, and then you can run different automation tools like static analysis and things to ensure whether the pipeline is correct, and many other optimizations. So moving on, I think I will pick 2 main elements out of this diagram, because rest of them seem they're not that straightforward, but they are relatively straightforward. But the 2 things that are actually new and are not handled by the OVS match action pipeline are the addition of arbitrary headers and removal of them, and then doing deparsing in the fast path. So let's see how we augmented the OVS Datapath. OVS fast path to actually accommodate for these changes. So P4 provides you some primitive actions for adding and removing headers. These are add header and remove header. Again, these are necessary for doing applications like encapsulation and decapsulation. Again, we are talking about programmable encapsulation and decapsulation. So it's like using these actions, you should be able to build any kind of protocol like VXLAN, VLAN, or any other type of tunneling protocol. And then there is a final thing, which is deparser, that operates, that sits usually at the end of the pipeline, and then serializes the packet into the final bit stream, which then goes out of the switch. Okay, so in OVS, at the moment, like currently how OVS operates is like, this is the fast path action block that I'm showing you here. So what happens, you got a hit in the cache. You came in here, and normally what happens is the packet goes through a series of actions, and these actions are mostly set field operations that are applied directly onto the packet. And then finally, once the last action has been applied, the packet goes out. But the problem is, in P4, P4 has the notion of header valids. Like you can actually say this header is valid or invalid. So now the thing is, whenever a packet, whenever a header is valid, the deparser actually checks for that bit, and then if it's valid, those changes are actually written onto the packet. Otherwise, those changes are discarded. So now you can see, if we do multiple set field operations on the packet, and later on we find out at the deparsing stage that that header is invalid, so all those changes, we have to revert them back. But using the current model that we have, where we apply the changes directly onto the packet, it becomes hard to do this kind of reversion of the commits that you have done on the packet. So in order to support that, I think the way we have done is, we actually kept a separate copy of the flow in the data path, and then all the changes were actually applied on that flow, which contains the header information. And finally, when the packet reaches the deparsing stage, based on the validity of the header, like it's valid or not, the changes are actually read from the header and pushed onto the packet in the deparsing stage. So using this, we were actually able to add support for arbitrary addition of headers and removal of headers, so that we can. So there is a canonical example in P4, which is like mtag encapsulation and decapsulation. So those kind of things become easier and can now be done by the pipeline itself, rather than using specific, like special Ethernet interfaces like for Geneve or VXLAN and things like that. Okay, so that was the first aspect, like mapping P4 to OVS. So we think it's we can actually take a P4 program and compile it onto OVS. But now the question comes up: what is the effect of that programmability on performance? So there are three different elements that we think are there in OVS that affect the performance. One is packet parsing, packet deparsing, and fast path actions. So now the thing is, in the existing OVS, number 2 and number 3, packet deparsing and fast path actions, they don't have that dominant effect, because fast path actions are mostly restricted to set fields, which are the write operations on the packet. And there is no notion of deparsing, because these changes are directly committed onto the packet. However, using the P4-like model, these are become more significant, because now you are actually doing changes on a separate set of headers, and then you are doing some kind of memory copy operation at the very end when you are doing the deparsing. And similarly, in P4, fast path actions become more complicated. Like it assumes this model that you do verify checksum at the very beginning, and then you do updates for the checksum at the very end. So instead of doing incremental checksum, you are doing full-blown IP checksum or other kind of hash actions at these two ends of the pipeline. Okay, so in order to show like what was the cost of programmability on performance, we actually ran this through a test bed. So our test bed was actually consisted of two systems, Haswell-based Intel Xeon systems. One was running OVS DPDK-based implementation with our modifications, and the second one was running packetgen to generate at least 10 gig line rate traffic. And then what we did was we tested this using two of the programs that are provided in the P4 Lang repository. One is the layer 2 learning switch, and the second was the layer 3 simple router. So we ran them through our compiler, we did some performance measurements, and then what we found is, again, because we added so much logic in the data path, the performance has to go down. But here we actually, let us explore this and why this is happening and what we can do to actually optimize this. So in the layer 2 learning switch, we see that vanilla OVS, which is the existing OVS, is performing around 10 gig for all packet sizes. But for the simple router, because we added parsing for IP headers, we see that there is a small dip in the small packet sizes for the vanilla OVS. However, this effect is actually more significant for the P4 OVS implementation. And please note, this implementation is actually based on a non-optimized compilation, where we actually didn't do any optimization in our compiler. We just took the P4 program and we compiled it to the OVS as is. Okay, so in that case, what we saw is so for the layer 2 learning switch, because the packet is coming in, and now instead of making just one copy for the slow path, we are actually keeping a separate copy for the data path. And then we are applying our changes and then finally doing a deparsing. at the very end of the pipeline. So that's why we see that for small packet sizes, the performance is actually much less than the one that we saw for the vanilla OVS. Similarly, for the simple router, there are two things that are affecting the performance. So again, one is the packet parsing and deparsing, and the second is the fast path actions that we had. Again, the blue line in the middle shows you like, again, it's a non-realistic example because we just dropped the checksum operations. And so just to see what is the difference in the performance. So by just removing the checksum operations, we saw that there is a significant, not that significant, but still a relatively significant amount of improvement in the overall performance for different packet sizes. Still, the main bottleneck is the packet parsing and the deparsing part of the logic, of the compilation. Okay, so now as a future work, what we are thinking about is, like, given that these are the baseline values we have for a non-optimized implementation, can we optimize them? Yes, I think we can, because P4 is a program that is already telling you most of the stuff about how it wants to process the packets. So for example, in the case of layer 2 switch, we know that we are not doing any modifications on the packet, and we are not doing any in-cap or decap. So based on that knowledge, we can simply optimize, we can let the compiler know that based on this information, just don't make this copy in the data path because it's never going to be used. Apply the changes directly onto the packet. So this way, we can actually improve the performance back to the vanilla OVS. However, in the case of simple routing, this might not be that straightforward because now you have to do a liveness analysis and to see which fields are being modified. So in this example, we are modifying the TTL, we are modifying the checksum. So again, rather than keeping a full copy of the headers in the fast path, we can actually just keep the copy for these individual fields and then put them back at the very end. So again, as a future work, we are actually working on implementing optimizations to avoid these extra copies of headers in the fast path. We are trying to look into traditional compiler optimizations like dead code elimination and liveness analysis to see how we can actually leverage them to improve the performance for this compiler. And then the other thing that I haven't actually focused much about is the support for general fast path actions like add to field. Right now, these actions are actually converted into set field operations when you're installing them in the cache. So for example, if you want to do a decrement on a TTL, you match on a value of a TTL, say 64, and then you set it to 63. So semantically, you are doing a decrement. But again, because we know the entropy of the TTL value is per connection, so it's doable. But for some other fields that have a high entropy, this thing might not be doable. So this is something that we are looking into as the next step as well. I think with this, I will conclude my talk, and thank you. Any questions?
Hi, I'm wondering why you need to modify the data path at all. For example, OpenFlow has also a concept of deferred action, which are deferred to the end of the pipeline, which is the action set. You write to the action set, and when you finish the pipeline, those are applied. And that was entirely implemented by Ben in the slow path. As you prepare your flow, you compute, you do all those things, and you resolve the set of action based on that. And it seems that you could do the same, which is as you compute the fast path flow, you resolve all those things so you have no data path changes.
Exactly. So the thing is, like, for the kind of actions that OpenFlow provides, again, this is the kind of optimization we can look at. But the implementation that we have right now is actually mimicking the model that P4 has onto OVS. So that's why you see this bottleneck.
No, but your model, you could do the same optimization,
right?
Which is, it's just deferred action. So you could resolve that in the slow path and only put what matters in the fast path.
Exactly. But the thing is, in the case of in-cap and decap, this is not that trivial.
On-cap and decap is another matter.
Yeah. So the thing is, like, because we are talking about a programmable compiler, we have to take care of all these possible cases and then pick the optimizations we can apply in the mix of these programs.
Yeah, but that would solve all the parse and deparse. You would eliminate the parse and deparse.
Yeah. But again, if you're not doing in-cap and decap, yes, you can eliminate that.
Hi, in P4, a field can be, this is a question. Can a field be a displacement plus a length, basically any arbitrary spot in the packet?
I think not in the P4 v1.0 spec, I think it's not the case, but they are looking into like handling Geneve-like options in the version 1.1. So this is actually based on the version 1.0 work that we did.
Yeah,
So,
I'm on the P4 design committee, and we've added things to support generic TLVs.
Yeah, I was just thinking of be able to, the limitation of Open vSwitch to so many matching fields. And there's always other things people want to match on. And I just see that as a tremendous potential of P4.
right, yeah.
Also, were your performance numbers, was that the Linux data path, Linux kernel data path, or was it DPDK?
It's DPDK.
Oh, okay,
yeah.
that explains. All right, thanks.
Right.
I think we have time for another question if anybody has one. So just to add a personal note, I'm really excited about the possibility of combining P4 with Open vSwitch. I gave a talk about a prototype implementation that I built of that. I think that was about 6 months ago at the first P4 workshop. Did they record those talks?
I don't. They have slides, but they don't. I don't think they recorded.
Ah, okay. Well, that's too bad.
Yeah.
But I'm really glad that Shahbaz is carrying the ideas forward. Let's thank our speaker again.
Right. Thank you.